in this video, we're going to look at the second part of this question. We have already worked out the compression ratio, which I think we worked out to be 2.05. We worked out the efficiency to be 44%, and we worked out the specific work, and the specific energy we worked out to be 150 kilojoules per kilogram. And the last part of the question is to calculate the compressor slip. Okay, so just quickly go through these slides. That's how we got the compression ratio. That's how we calculated the efficiency of the compressor, and then we worked out the specific work. So the next part of the question is to work out what the slip is. So we were told that the compressor was rotating at 116,200 RPM, and if we have that, so that's N. So revs per minute divided by 60 brings in revs per second, and multiply that by 2 pi will give us the radians per second. So the compressor here is rotating at 12,168 radians per second. The velocity here at the tip, or at the blade exit, so the velocity here is going to be omega r. And in the question we were told that the radius, this radius here, was 50 millimeters. So the velocity at the blade exit is going to be 1216 times 50 millimeters, which is 0.05 meters, which is 608 meters per second. The work in must equal the work out, and the mass of air coming in must equal to the mass of air going out. So these two values are going to cancel out, and we're left at Cp times T3 minus 2 is equal to VBE squared times sigma. So this is 1005. We calculated, we were given the temperature as 440, and temperature coming in is 290. And that worked out to be 150 kilojoules per kilogram. That should be equal to 608 squared times sigma. So 150 K is equal to 608 squared times sigma. And then when we rearrange that, so we divide 150,000 by 608 squared, we get 0.4. So we get a slip value of 40%, which again is pretty poor, but that is just for this demonstration type gas turbine.